Welcome to this lecture on sampling distributions. Today we are going to explore the F distribution. We will build our understanding from the ground up, starting with why we need it, how it is mathematically defined, and finally, how we derive its probability density function. Let us dive in. Imagine you are managing two different factories that produce the exact same type of light bulb. You want to know if one factory's manufacturing process is more consistent than the other. To figure this out, you cannot just look at the average lifespan. You have to compare the spread or variance. The most natural way to compare two positive numbers is to divide one by the other to see their ratio. If the ratio is close to 1, the factories have similar consistency. If it is very large or small, one is much more variable. The mathematical tool we use to understand this ratio is called the F distribution. Now that we understand why we need this ratio, let us look at its formal mathematical definition. In statistics, the F distribution is defined as the ratio of two independent chi-square random variables, where each is divided by its own degrees of freedom. Here, U and V are our chi-square variables, representing sums of squared standard normal variables. The terms N1 and N2 are their respective degrees of freedom, which represent the number of independent pieces of information. By dividing by the degrees of freedom, we standardize the values. Because variances are always positive, the F statistic will only take on positive values. This formula we just saw leads us to an important question. What does the exact mathematical curve of this distribution look like? To find out, we must perform a derivation. We start with the knowledge that our two chi-square variables u and v are completely independent. Because of this independence, the combined probability of both happening at the same time is simply the product of their individual probabilities. When we multiply the chi-square formula for u and the chi-square formula for v, we get this intimidating but essential joint probability density function. The gamma symbols represent continuous factorials, ensuring the total probability area equals exactly 1. Moving forward with our derivation, we need to change our variables from u and v into the variables we actually care about, the ratio f and a dummy variable w. We define w as being equal to v, which allows us to express u in terms of f and w. In calculus, when we change variables like this, we must also multiply by a scaling factor called the Jacobian determinant. This Jacobian ensures that the total probability remains exactly 100% when we stretch and squeeze our coordinate system. Taking the partial derivative of u with respect to f gives us our Jacobian, which is n1 divided by n2 times w. To reach our final result, we substitute our new expressions into the joint probability function. However, we only care about the distribution of the ratio f, so we want to completely ignore the dummy variable w. In probability, to remove an unwanted continuous variable, we must integrate it out over all its possible values, from 0 to infinity. This calculus step collapses our two-dimensional formula down into a one-dimensional formula for f alone. This final result is the probability density function of the F distribution. As f gets very large, the denominator grows much faster than the numerator, causing a probability to approach 0. Now that we have derived the complex formula, let us visualize what it actually looks like. Here we see the F distribution probability density curves. The horizontal axis represents the calculated F value, and the vertical axis is the probability density. Notice that the curves start at 0. They never go into the negative numbers because variances are always positive. You can clearly see the long right tail we mentioned earlier, showing that extremely large variances are rare. The shape of the curve changes dramatically depending on the degrees of freedom. As the degrees of freedom increase, the curve becomes tighter and starts to look a bit more symmetric, peaking closer to an F value of 1. Having seen the shape of the distribution, let us explore one of its most important practical applications, the two-sample variance test. This test is used when we want to check if the variances of two different populations are equal. We start by assuming that the true population variances are exactly equal. When we do this, a magical cancellation happens in our math. The theoretical population variances cancel out completely, leaving us with a ratio that depends entirely on the sample variances we actually measured from our data. If our calculated ratio is very far from 1, it gives us strong evidence that our initial assumption was wrong and the populations are actually different. This brings us to the simplified formula for the two-sample variance test. Because the population variance is cancelled out, our test statistic F is simply the sample variance of the first group divided by the sample variance of the second group. Here, S1 squared represents the variance calculated from our first sample, and S2 squared represents the variance from our second sample. Under the assumption that the true population variances are equal, this ratio perfectly follows an F distribution. If the numerator is much larger than the denominator, the F value increases, signaling a significant difference between the two groups. Before we move on, let us see this with a concrete example. Suppose a teacher wants to know if two different teaching methods result in different levels of consistency in student test scores. She tests 10 students using method A and finds a sample variance of 15. She tests 12 students using method B and finds a sample variance of 5. We need to calculate the F statistic. We will place the larger variance in the numerator to ensure our F value is greater than 1, making it easier to look up in statistical tables. We substitute 15 for the numerator and 5 for the denominator. Continuing with our calculation, we simply perform the division of 15 by 5. This gives us a calculated F statistic of exactly 3. Physically, this means the variance in test scores for method A is exactly 3 times larger than the variance for method B. To make a final scientific conclusion, the teacher would compare this value of 3 to a critical value from an F distribution table. She would use 9 degrees of freedom for the numerator, since 10 minus 1 is 9, and 11 degrees of freedom for the denominator, since 12 minus 1 is 11. Now that we have used this formula, let us explore a beautiful and deeply fundamental connection between the F distribution and another famous statistical tool, the student's T distribution. The T distribution is typically used for testing means when the sample size is small. It turns out that if you take a random variable that follows a T distribution and simply square it, the resulting value perfectly follows an F distribution. This happens because squaring the T variable's fraction creates a squared standard normal in the numerator and removes the square root from the chi-square in the denominator. This perfectly matches the definition of an F distribution. Let us look at the mathematical formula for this relationship. The formula states that T squared follows an F distribution with 1 and n degrees of freedom. Here, T represents a value from the student's T distribution with n degrees of freedom. When we square it, the numerator becomes a chi-square variable with exactly 1 degree of freedom. Therefore, the squared T statistic is mathematically identical to an F statistic that has exactly 1 degree of freedom in the numerator and n degrees of freedom in the denominator. This is why tests for means and tests for variances often yield mathematically equivalent results. Let us see this connection in action with an example. Suppose a researcher conducts a standard t-test to compare a sample mean against a known population mean. The sample size is 11, meaning there are 10 degrees of freedom. The researcher calculates a t-statistic of 2.5. We want to demonstrate the mathematical connection by converting this t-statistic into an equivalent F statistic. To find the equivalent F statistic, we rely on our fundamental theorem. We simply need to square the given t-value. We substitute the researcher's calculated t-value of 2.5 into the equation. Continuing from our substitution, the next step is to multiply 2.5 by itself. This gives us a final equivalent F statistic of 6.25. This value belongs to an F distribution with 1 degree of freedom in the numerator and 10 degrees of freedom in the denominator. If the researcher looked up the p-value for 2.5 in a t-table, it would be exactly identical to the p-value for 6.25 in an f-table. This proves that both tests lead to the exact same scientific conclusion. So, we have proven that the F distribution connects deeply to other statistical tools. This brings us to its most powerful application, ANOVA, which stands for Analysis of Variance. Whenever scientists or medical researchers need to compare the results of 3 or more different groups at the same time, like testing 3 different blood pressure medications, they use ANOVA. Without the F distribution, we would be forced to run dozens of individual tests, which drastically increases the chance of making a false discovery. The F distribution elegantly compares the signal between groups to the noise within groups in a single ratio. Let us review the key takeaways from our lecture. We learned that the F distribution provides the exact mathematical probabilities for the ratio of 2 independent variances. We successfully derived its complex probability density function by starting with 2 independent chi-square variables and using calculus to integrate out the unwanted variable. We saw how it is practically applied in the 2-sample variance test to compare consistency. We also uncovered its beautiful connection to the t-distribution. You have now covered the full topic, understanding one of the most powerful tools for analyzing variability in the real world.